Hi, I am Chih-Shen. I'm currently a PhD candidate at Texas A&M University. The research topic I'm going to present is a Bayesian framework for human-AI partnership in disaster damage classification. So let's start with the motivation. Recently, natural hazards and disasters have severely impact our living world, causing significant economic and fatal losses. After these disasters, damage assessment and disaster impact analysis are key to successful disaster response and recovery. However, the problem is that the human-based damage assessment is risky and time-consuming. The trade-off between speed, safety, and accuracy have motivated new practices of damage assessment using remote sensing and artificial intelligence, AI. However, AI makes mistakes and unreliable predictions, and ignoring the uncertainty may lead to error decision-making with serious outcomes. In addition to AI, a crowdsourcing platform, for example, Amazon Turk, social networking system, also present a great opportunity for rapid post-disaster damage assessment from the crowd. And humans expect to perform damage assessment more reliably than AI, since they often have some level of background knowledge of the scenes in disaster-affected areas. However, crowd-based damage assessment is also prone to uncertainty and requires special attention to the reliability of annotators. As another limitation, crowd-based damage assessment is resource-intensive and costly due to the large amount of information that must be processed to complete the damage assessment test from the crowd. With these motivations, the objective of this work is to develop a crowd AI framework that integrates the power of AI with human intelligence from the crowd to reduce the uncertainty and increase the consistency in post-disaster damage assessment. And let's look into the figure which visualizes the crowd AI framework. And there are two modules of this framework. One is Deep-PDA. Deep-PDA focuses on performing uncertainty-aware building damage assessment using Bayesian deep learning model. And this model is designed to simultaneously predict the damage level and quantify their underlying uncertainty. Another module is named crowd-PDA, a probabilistic crowd-based module for reliable participatory damage assessment. Again, humans are expected to perform more reliably than AI. And the goal of this crowd-PDA is to reduce the uncertainty produced by Deep-PDA module. Let me briefly talk about what is Bayesian deep learning. And in Bayesian neural network, the weights are random variables, which means that the predictions are also non-deterministic or stochastic. And the target is to inference the probability of the weight given the data based on this Bayes rule. And after the model training, the model can make inference by outputting the damage level prediction and its underlying uncertainty. And in this study, we use entropy, this metric, to quantify the uncertainty rigorously. So the second model performs crowd-based participatory damage assessment. The name of this module is, again, is crowd-PDA. And crowd-PDA aims to reduce the uncertainty produced by the Deep-PDA module. So given the data annotation from crowd workers, we can use maximum posterior probability MAP model to inference the building damage severity, the difficulty of each labeling text, and most importantly, the collective probabilistic label for each building or images simultaneously. And here are mathematical description of the probabilistic inference of crowd-PDA. And here is the logistic regression model formulation, and on the left, and the likelihood function is shown on the right-hand side. In particular, we account for the participants' general ability using theta, and the general difficulty of the classification text using xi. And so we use expectation maximization, EM algorithm, to obtain the unobserved or latent variable z, theta, and the xi variables. And how these two models collaborate with each other. So we know that crowd-PDA is to help to resolve and reduce the uncertainty from Deep-PDA. So we define a threshold to determine whether it is required to use crowd-PDA to resolve the uncertainty. And in this case, in this formula, C is a uncertainty tolerance, and this C can be defined by the users. For example, the smaller C value means that the threshold is lower, and more texts are needed to be from the crowd-PDA to resolve the uncertainty, which also suggests more crowd-PDA effort or cost. Also, we will use AI damage assessment output as a prior for the input of the crowd-PDA. So these prior probabilities from AI are useful when the ground truths of the buildings are known at some certain level. And let's move on to a case study. So in this case study, the Dorende dataset is used to train the Deep-PDA module, and 100 building samples are selected and used in this case study, and 20 crowd workers are recruited to label the damage severity from the crowd. So for the model setting, we use C is equal to 0. The uncertainty tolerance is 0. And in this situation, 51 cases out of 100 are selected for crowd-PDA using the threshold that we defined previously. The result shows that the crowd-PDA is capable of solving the cases with high uncertainty, and after crowd-PDA for reducing the uncertainty, we can notice that most of the probabilities that are aggregated into 1 or 2 damage level classes as shown on the left-hand side. So in this figure, the x-axis is the entropy. So it can be noticed that the average entropy from the PDA prediction is reduced by around 30%. And also it is noticed that both the entropy values and the variation of the entropy are significantly reduced after using crowd-PDA. So here's the results and discussion. So the performance of the model is 36% for Deep-PDA and is 48% for hybrid crowd AI framework, and which is 33% improvement. Also, the uncertainty is decreased using the hybrid system by around 30%. Also, we conduct the sensitivity analysis of the uncertainty tolerance, the C here. This is used to define the threshold for this hybrid system. And let's look at the figure on the right-hand side. The x-axis is the C value, and y-axis are number of selected tags for crowd-PDA and MB. And large MB means that the higher cost or effort from crowdsourcing. And the overall uncertainty of the framework is on the right side of the y-axis. Overall, the smaller C value can further reduce the uncertainty using the hybrid framework, but suggests a higher cost of crowdsourcing. So idea of the choice of C is that the user will have to make sure that again, in the uncertainty reduction with additional crowd-PDA efforts should be significant enough to offset the cost of crowd-PDA adoption. So finally, is the summary and contributions of this work. And first of all, a novel probabilistic hybrid crowd AI framework was introduced to improve the reliability and reduce uncertainty in AI-assist post-disaster damage assessment. And the framework consists of two modules. One is Deep-PDA, and the second module is crowd-PDA. And the hybrid system resulted in about 33% high accuracy and 30% reduction in uncertainty as compared to a single Deep-PDA module. And this hybrid crowd AI framework can enhance PDA practice and support the post-disaster decision-making by providing more reliable and consistent damage assessment outcomes. I'm near to the end of the presentation, and thank you very much for your attention.